Now, let's talk about cutting planes, right? So I said in the state-of-the-art mixed integer linear programming solvers, a branch and cut was used, right? Branch and cut is a combination of branch and bound and cutting plane methods. But for many decades, these two algorithms are used separately, right? If cutting planes, I think, were developed in the 60s or 50s, most people would treat cutting planes as a pure theoretical interest. It's not practical to implement for many decades. On the other hand, branch and bound was faster than pure cutting planes. But branch and bound is a very pedestrian approach per se, right? When you listen to the previous lecture, we basically covered most of the concept, most of the algorithm in branch and bound in a single lecture. But if you want to study all the theory related to cutting planes, that will be at least 1 or 2 semesters, right? But it was not until in the 90s when the solver Cplex started implementing cutting plane into its branch and bound algorithm. Then people realized that cutting planes were actually useful, right? For many decades, people thought it's just like theoretical curiosity. So this figure showed the speed up from one version to another Cplex, right? So this was version 6.0 of Cplex, and this was like 12.5, right? Basically, they update the solver basically every year, right? And then version 6.5 is when Cplex started to add cutting planes, and they got around 5 times speed up, right, by adding cutting planes. And over the years, as you can see, the solver get improved by quite a lot, right? On the right-hand side, you see the total speed up from version 6 to version 12.5 in total. This is just accounting for the speed up from the algorithm itself, not accounting for the speed up from computers, right? It will not be fair. So then the total speed up is 90 times over the range of around 6 years. Of course, over the years, it got way more speed up than just 90 times. So therefore, it kind of showed the cutting planes are still useful, right? So we'll spend one lecture talking about cutting planes. It is not possible to derive all the theory related to cutting planes in one lecture, right? If you want to read this whole integer programming book, most of the chapters are about valid inequalities, cutting planes, relaxations, right? It probably accounts for over 95% of the integer programming book, and branch and bound is just a few pages. It's very, very easy to understand branch and bound. Therefore, in this lecture, we will only focus on the intuition of cutting planes. Most of the theory will be given without any proof, right? I will sort of give you an intuition of the theorems. If you are interested in how to prove that, you can read the integer programming book. Okay, and then you can apply these cutting planes to some very small toy problem just to appreciate sort of the beauty of this theory. Okay, this figure may still be familiar to you. As you can see, we have the MLP feasible region, right? And then if you take the LP relaxation, maybe you got this extreme point and it doesn't satisfy the inequality constraints. And then if you can add a cutting plane that cut off a huge chunk of this feasible region, then you can have a tighter relaxation by adding the cutting plane. Yeah. And how do we derive the cutting planes, right? They are usually derived by the fact that some of the variables are integer, right? So this sentence is kind of redundant. Of course, if you derive something not taking into the fact that some of the variables are integer, you are not going to derive any new inequalities compared with the linear programming relaxation itself, right? So in other words, the cutting planes cannot be derived from the LP relaxation, right? The inequalities derived from LP relaxation will not improve the LP relaxation itself, right? So therefore, you have to take into account the fact that some of the variables are integer. And the major technique used to derive cutting planes is rounding. So rounding means you can round a variable to be integer if they are fractional. Right? So, and then some of the cutting planes are derived from, let's say, logic. Right? So I will show you some examples of different types of cutting planes. Some are derived from the logic related to the problem. Some of them are just derived from rounding. Okay. Yeah, so here, besides the geometric motivation, these theorems shows you a theoretical motivation why cutting planes can be useful, or why getting the convex hull of a given optimization problem can be useful, right? So the theorem says the following. If you are solving a, let's say, supremum, or you can think about this as a maximization problem, is if S is a compact set. So if you have C transpose X, subject to X is in a set S, right? So S might be a non-convex set, like S might represent an MILP or a mixed integer nonlinear program or a non-convex program. And solving this problem is equal to, the objective is equal to supremum of C transpose X. X is in the convex hull of set S. Right? So this is without loss of generality. S can be any set. Right? So if you solve, let's say this is a non-convex optimization problem, the objective will be equal to a convex optimization problem, which says X is in the convex hull of S. Right? And of course, getting the convex hull is not trivial, right? Since convex problem can be solved in polynomial time, and then non-convex problem usually is not polynomially solvable, now you know something is conflicting, right? So that means getting the convex hull or describing the convex hull can be very hard. You might need things like an exponential number of cutting planes to describe the convex hull. Okay, so that's sort of the interpretation of this theorem. If you have an MILP and then you can get the convex hull of an MILP, then it will be equivalent to solving an LP, or maybe the any ways that can describe the convex hull of the MILP, right? But it doesn't tell you how to get the convex hull. It just shows if you can get the convex hull, this problem will be equivalent to the original problem. That's why you are motivated to get the convex hull, right? Okay. Now, because we are interested in getting the convex hull of integer linear program or mixed integer linear programs, we might be wondering how to describe the convex hull, right? So this theorem called Mayer's theorem is a so-called fundamental theorem of integer programming, right? So if you want to remember one theorem in integer programming, this might be of interest. Okay, so let's say don't take a look at the math, right? So let's think about how will the convex hull of an integer linear program look like, right? So if you look at this picture, the original problem is MILP, or actually an integer linear program. There is no continuous variable, right? And the convex hull is this yellow region, dark yellow region here, right? So here the convex hull is a polyhedral set, right? So the original problem is a polyhedral set intersected with integrality constraints. And the convex hull can be described by a polyhedral set, right? Or linear inequalities. So this observation is actually general for any mixed integer linear programs. Basically, Mayer's theorems is saying if you have a rational matrices A and G and rational vector B, and it is described by, the problem is described by AX plus GY less than or equal to B, and then let the set S be XY in the polyhedral set P and X being integral, right? So this is, set S is basically a mixed integer set, right? Y is a continuous variable, X being the integral variable, right? It's a general mixed integer linear program set, right? So the theorem says if you want to describe the convex hull of S, it can be described by a polyhedral set, right? A prime x plus g prime y less than or equal to b prime, and all those matrix and vector entries are rational numbers. Right? Again, Mayer's theorem is not an algorithm. It's just an existence theorem. Right? It says for any mixed integer linear programs whose data are described by rational numbers, its convex hull is a polyhedral set. Right? And then all the entries of the matrices and vectors are also rational numbers. It is an existence theorem. Right? So what's the implication of this is that if you want to find the convex hull of mixed integer linear programs, it will be sufficient to use linear inequalities. Right? You don't need to describe the convex hull using nonlinear inequalities. Right? So it basically says linear inequalities will be sufficient to describe the convex hull of an MILP. Okay. And then if the polyhedral is unbounded, it says the recession cone of convex hull and the recession cone of this polyhedral set P are the same. Right? Okay, so that's basically, if you look at this set here, right? So this is the relaxation. And the recession cone would be the cone that you can extend to infinity, right? So the recession cone of the convex hull and the recession cone of P coincide in this case. But for most of the problem, you can imagine we are dealing with bounded problem. You can just think about the convex hull can be described by a bounded polyhedral. Okay. Now, any questions here? Right. So just a theoretical background, say the convex hull exists and it's a polyhedral set. Now let's go over a few very trivial examples, sort of to build up our intuition. Right? The first few examples I gave will be related to deriving deriving some valid inequalities or cutting planes from logic, right? So based on your intuition, you can already derive these inequalities, just based on the fact these some of the variables are binary, right? So here we have a set we see very often in integer program. It has a big M constraint, right? So you can think about the 9999 as the big M number here, right? So y is less than or equal to 9,999 times x, and y is between 0 and 5. X is a binary variable. Okay. So from all these constraints, it is easy to derive these inequalities that tightens the big M constraints, right? Because y is between 0 and 5, x can only take values 0 or 1. Then you can derive this inequality that is tighter than this big M constraint, right? Okay, because when x equals to 1, and then y can at most be 5, therefore you can derive this inequality. Now the question is, let's think about this for a second. Can this inequality be derived based on the LP relaxation? Right? Let's suppose I don't have x in 0, 1. Let's assume we have x is a continuous variable between 0 and 1, right? Then the question is, can you derive y less than or equal to 5 from these linear inequalities? Or if not, you can show me a counterexample where this inequality is violated by some feasible point in the LP relaxation. Yeah, so 0.1 and 5, right? Okay. So let's say x equals to 0.1, y equals to 5. Right? If you check this point, it is clearly feasible for this big M constraint, right? Because 0.1 times x 9999 times 0.1 is 999.9, right? And clearly, since y equals to 0.5, the first inequality is satisfied by 0.1 and 5, right? And then the second inequality is also satisfied, x is also satisfied. But 0.1 and 5 clearly violates this inequality, right? So that's why you, in order to derive this inequality, you have to take into account the fact x is a binary variable, right? And then if you take into account x is a binary variable, you are likely to derive some tighter inequalities than the LP relaxation, right? You cannot really derive something tighter than the LP relaxation from the LP relaxation. Okay. Yeah, so here's another example related to the facility location problem. And this is called capacitative facility location problem. Just recall the definition of the facility location problem. Okay, you have some customers denoted by I belongs to the set M, and you need to build some facility to satisfy the demand of the customers, right? And then you have n different locations to build those facility. Let's assume the capacity of the facility is Bj, right? Maybe you could, let's say these are the customers you plan to serve, and then let's assume you could build 2 facilities, and then the capacity of the facility is B1 and B2, and then the demand of these customers are A1, A2, and A3, right? So you could build both facilities or one of those facilities in order to satisfy the demand of the 3 customers, okay? So the equations are the following, right? If you build this facility, xj will be equal to 1, right? And the left-hand side basically sums over the demand of customer I that is satisfied by facility j, okay? So yj is the demand of customer I satisfied by right, and then if this facility J is not built, then all those demands should be 0, right? Because if the facility is not built, none of the customers can satisfy the demand through facility J. Here it says, if you sum over Yij over all the facilities, it has to satisfy the demand of the ith customer, okay? So from that, we can easily derive some valid inequalities taking into the account xj is a 0, 1 variable, okay? So it's very clear that these 2 inequalities are satisfied, right? So why this inequality is true, right? The first inequality. Right, so this is basically saying the demand satisfied by facility J, right? The customer's ith demand satisfied by facility J is less than or equal to the capacity of the facility J times xj, right? This is clearly true because you can think about Yij as, yeah, so Aj, okay, so this is a facility, and then okay, so the 3 customers need to be the demand of the 3 customers satisfied by facility 1 is denoted by y, in this case, I1, right? And of course, they cannot exceed the total capacity of the facility you have, right? And similarly, the demand you satisfy by facility J has to be less than or equal to the total demand, right? AI is the total demand of a given customer, okay? And now with these two inequalities, it says this inequality is true, okay? So why is that? Yeah.
I'm sorry, why can Yij be less than AI in this case if I thought they would have to be, I guess, strictly equal?
Yeah, so less than or equal to AI. I mean, let's say if you have a given customer here and then you only have one facility, right? Then the total demand is satisfied by one facility. Then in this case, it's equal, right?
Yeah.
Right. But then, of course, the Yij has to be less than or equal to AI because the total demand is AI.
Oh, okay.
Yeah, yeah.
So that's like for multiple facilities would be the median, right?
Right.
Okay, makes sense.
Okay. Yeah.
Understanding that upper bound.
Yeah, so this is the same thing as this big M type of constraint, right? In this case, the B is the big M here, right? And A is the upper bound of Yij. Okay, yeah. Okay, so let's give one more example derived from logic. So it's called the stable sets problem. If you haven't studied graph theory before, let's talk about two concepts. One is called stable sets. The other is called the clique of a graph. Okay. So consider a graph. A stable set means pick a subset of vertices in a graph such that no two of which are adjacent. Okay. Let's maybe pick a trivial example to explain this concept. Yeah. Okay, let's draw some edges. Okay, here. So now this is a graph, right? We have 5 nodes, and then I randomly drew some edges, right? So a stable set is a subset of the nodes. So let's pick a subset of the nodes, maybe this particular node and this particular node here, right? So these 2 nodes is a subset of the 5 nodes, and I call these 2 nodes a stable set of the graph because these 2 nodes are not connected. Okay, there doesn't exist any edges that connect these 2 nodes, right? And actually, if you want to pick many nodes, there shouldn't be any edges connecting any of the 2 nodes. And that's called a stable set. But then if you pick some other, some other let's say if we pick these 2 nodes, then they are connected, right? This is not a stable set. Okay. And then the second thing we should talk about is what is called a clique. So a clique of a graph means if you take a subset of the nodes, there exists an edge between any 2 nodes you pick in this subset. Okay, so let's explain what is a clique. So here's another graph, okay? So I say these 3 nodes is a clique of the graph because you pick any 2 nodes from the 3 nodes, they are connected by an edge. Or in other words, this subset of nodes are fully connected, okay? So that's called a clique. Yeah. Now, what is clique inequality? Right. The idea here is we need to consider a set of vertices in a graph such that they form a stable set. Right? So in order to form a stable set, it is very easy to understand that this inequality has to be satisfied. Right? So x equals to 0, 1, we have a 0, 1 variable for each vertex in the graph. Okay. And since for any nodes that are connected by an edge, only one of them should be in the stable set, right? Because in a stable set, any of the two nodes cannot be connected. Okay, so that's why we have this inequality here, in order for the subset of nodes you pick to be a stable set. You look a bit confused. Maybe someone should ask a question. Yes?
So the xi and xj, those are edges that we're looking at.
Xi, xj are nodes.
Okay, so they're nodes, but then it says that the I and j are elements
of the edges, right? So is a set of all the edges, right? So when the I and j's are the nodes that are connected by an edge.
Oh, I see.
All right.
Okay.
Okay, so if two nodes, E is a set of edges, right? So if I and j is in the set of edges, right, then only one of these nodes can be in the stable set, right? Because any nodes in the stable set cannot be connected, right? If they are both in the stable set, then they are connected by an edge. That's not a stable set. Okay, yeah. So that's sort of the definition of a stable set, right? Now. The clique inequalities means if U is a clique of V, then that means, by definition, a clique means there exists an edge between any pair of nodes in U. Okay. So then we have this inequality is valid. The summation of all the nodes in the clique has to be less than or equal to 1. Okay, why that is the case? Just like in this case, right? We have these three nodes being a clique, right? So that says at most one of these nodes can be in the stable set. Yes?
To be a stable set, they can't be connected to each other since everything in U is connected.
Yeah, exactly right. So it is derived from the logic that in a clique, any two nodes are connected, right? So if one nodes are in the stable set, all the other nodes cannot be in the stable set because all the nodes are fully connected, right? So that's why you can at most select one of the nodes in the stable in the clique, right? In order for the subset you select to be a stable set. Okay. This is called the clique inequality, right? So as you can see, the clique inequalities is stronger than the inequalities you have on the edge, right? Because here, let's assume you have x1, x2, x3, x4, right? So the clique inequality will look like x1 plus x2 plus x3 less than or equal to 1, right? So this inequality is stronger than the edge inequalities you could derive, right? Because in these inequalities related to the edge, you have two xi, xj's on the left-hand side, right? But in the clique inequalities, you have 3, right? You are increasing the number of xi, xj's on the left-hand side, right? So it is stronger than the edge inequality. Okay, and then if you have a very large clique, let's say 50 nodes that are fully connected, this inequality would be much stronger than the inequalities you derived here. Okay. Any questions here? Okay. Now, as you can see in the first few small examples, the rationale we used to derive the valid inequality is kind of from the logic of the problem, right? Like clique inequalities or rounding the big M. But then there are other inequalities or more general inequalities we can derive based on rounding some fractional variables. Okay, so in the next few slides, I will talk a few other valid inequalities. They are more general than the small examples we gave you. But then the fact that these inequalities are valid comes from very easy logic related to integer rounding. Okay. So before we generalize this concept, let's consider a small example here. Okay. So here, let's say we have 4 integer variables. Okay, x1, x2, x3, x4. They are all integer. We have x being greater than or equal to 0 as well. So x is greater than or equal to 0, non-negative integers. And we have this inequality here. So how do we derive a new inequalities from this inequality? Here's an example. Okay, let's derive these inequalities by 11. Then we get this inequality here. So here I did nothing but divided by 11. Yes.
Why did we choose 11 instead of like 20?
Yeah, that's a very good point, right? So we will show you later on how to derive a good coefficient. Actually, in most of the times, this inequality is derived from the simplex tableau. Because after you solve the LP, you find some of the variable to be fractional. Then you want to cut off that fractional variable from the optimal solution of the linear programs. Here it just shows you a random number on how do you derive this type of inequality. Right? Without loss of, you can choose 20 and then use the same procedure and derive another inequality. Okay, yeah. So let's say we divide it by 11. Okay. So since all the x are non-negative, right? If I round up all these numbers, right? So x are non-negative, right? And then this is a greater than or equal to 0 inequality. If I round up all the numbers on the left-hand side, this inequality is still valid. Right? Because x is greater than or equal to, you multiply them by an even bigger number, it is still greater than or equal to the right-hand side, right? So this is the round up, right? You got 2x1, 2x2, x3 plus x4, right? It's just round up this coefficient, round up this number will be 2, okay? And it is a valid inequality, right? So now we have this particular inequality here. An observation here is all the coefficients and the numbers on the left-hand side are integer. Right? All the x are integer, and then all the coefficients are integer. So this whole thing on the left-hand side must be an integer. Right? On the right-hand side is not an integer. Since the left-hand side is an integer, the right-hand side is not an integer, I can round up the right-hand side, this inequality is still valid. Right? So with this round up, we got this inequality here, right? Because this is integer, then if an integer is greater than 6.5, that means this integer is greater than or equal to 7. Right? So that's what you got. Okay. Now, you don't need to know any sophisticated math to follow this. It's just using the fact all the x are integer. Right? If the left-hand side is fractional, you can round up the left-hand side and round up the right-hand side. Okay. Yeah. Now, how do you derive valid inequalities in general for integer programs, right? Here, what we did is we multiply this inequality by 1/11, right? But in general, you can derive any valid inequalities for the linear programming relaxation and then round up the left-hand side, round up the right-hand side, right? As long as this inequality is valid for the original inequalities. Yeah.
So isn't this a weaker constraint overall?
Sometimes it is weaker. Sometimes you will derive something new. Right? I will show you in the case of simplex test tableau, using this approach, you get a stronger inequality to cut off your optimal LP. Right? That's a very good point. If you do it randomly, you may not end up with a stronger inequality. Okay, yeah. But then in general, let's say how do we generalize this example, right? So the idea is let's derive some arbitrary valid inequality. This is a valid inequality for the linear programs, right? You multiply a linear constraint, right? So in general, you can derive any valid inequalities for the linear programs and then do this round up left-hand side, round up right-hand side, right? Any valid inequality, you can do that, right? So let's take a quick review on what is a valid inequalities for a linear program. Right? This is the something called theorem of alternative we discussed in the linear programming session, right? So if you have a linear program or a polyhedral set represented by ax less than or equal to b, x greater than or equal to 0. Right? The way you could derive a valid inequality is you pick some, this u and v are like your Lagrangian multiplier to aggregate the inequality constraints, right? So if you multiply this constraint by u and v such that u a, right, should be actually u transpose a minus v equals to pi, and then u transpose b less than or equal to pi 0, right? So then that is a valid inequality for the linear program, right? So again, intuitively, it's nothing but you have some coefficients to aggregate the constraints in the original linear program, right? In this case, in this trivial case, you multiply them by 1/11, right? You can have a coefficient for each inequality in the linear program, and then you do the rounding. Okay. So this can be represented as a general procedure. It is called a Schwartl-Gomery procedure to construct a valid inequality. Okay. So the idea is the following, right? I mean, the theory is quite complicated, but this procedure is very easy to understand. Okay, but what you will do for this set of inequality, right? You have ax less than or equal to b, x is greater than or equal to 0, right? And A is a m times n matrix with columns a1 all the way to an. Okay. Now, the idea is you would aggregate those inequalities by the vector u, right? So let's suppose u is the same dimension as the number of constraints, right? You will multiply each constraint by a coefficient ui, right? In total, you have m of those inequalities. Let's multiply by some coefficients to aggregate them into one inequality, right? And after the aggregation, what you got is essentially this, right? You multiply u to each column of the constraint. Okay. Now, with that, the coefficient of xj in this aggregated inequality is u times aj, right? And with the same rationale we discussed before, since x is an integer, right? You could, in this case, you have a less than equal to inequalities. If you round down the left-hand side coefficient, it is still valid, right? Since x is greater than or equal to 0, if you multiply x by a smaller number, it will be even smaller, and of course, it will be less than or equal to the right-hand side. You have a question?
Can we have a negative?
You cannot, because you want to keep the signs of this less than or equal to 0, right? In order to aggregate them. Oh, can you have a negative? Oh, sorry. Yeah. Oh, yeah. You can have a negative.
Then don't we have to round in a different direction? I mean, not round up, but round
Yeah,
down.
but all the x are greater than or equal to 0, right? So if you have, let's say, minus 3.5 times a positive number, right? Minus 4 times the number is also smaller, right? Yeah, because
it's still rounding up, but yeah.
Yeah. So because all the x are greater than or equal to 0. Right? Okay, so if you round down, it will become smaller since xj's are greater than or equal to 0, right? And follow the same rationale, you can also round down the right-hand side, right? Because the left-hand side is an integer. If the right-hand side is not an integer, then you could round it down, right? So this is a valid inequality for the original integer program. Okay. But how to pick the good u is not a trivial question, right? So let's assume theoretically you pick all the u's to be greater than all the possible u greater than 0, then you derive infinite number of inequalities here. Okay. So why is this interesting? There is a theorem saying that if you derive the valid inequalities in this procedure, right, you only need to apply this procedure a finite times to get all the potential valid inequalities for x. Right? In other words, you can get a convex hull of integer linear programs by applying the Schwartz-Montgomery procedure a finite number of times. Okay, it's just a theoretical result. Of course, you are now going to get all the possible u's to derive the Schwartz-Montgomery inequalities. Right, so that's why in practice, one will start with the LP relaxation of the integer linear program, and then apply a scheme called Gomery's fractional cutting plane algorithms. Okay, so let's just talk about this method and how to apply this Gomery cut. Okay. Now remember, in solving the linear programs, we assume we are writing the polyhedral set in this standard form. Right? X is greater than or equal to 0, ax equals to b. Right? And now if you are solving the LP relaxation of this problem, remember in simplex algorithm, we have something called the optimal basis, right? The basic variable, non-basic variable, and so forth. The basic variable is basically b inverse times the right-hand side, and all the non-basic variables are 0. Right? That's what we did in simplex algorithms. Now, in the simplex tableau, right, when you basically you can write just to refresh your memory, right? We have ax equals to b, right? And then let's assume b is the basis. B is a basis, and it corresponds to the non-basic variable, right? Okay, and then you multiply b inverse on both sides. Then what basically you get is maybe write it in a slightly nicer way. So b multiply the basic variable xb, and then xn represent the non-basic variable. Okay. And then you could also write it as the basis matrix times xb plus the non-basic matrix times the xn equals to b, right? And then you multiply b inverse on both sides. What we got is xb plus b inverse times the n xn equals to b inverse b, right? So at this basis b, xb equals to b inverse times b, all the xn equals to 0. Right? That's what we did in simplex algorithm. So let's suppose you already solved the LP to optimality, then each row of this what is called a simplex tableau looks like something like this, right? So because here you have xb here, basically you have a diagonal identity matrix times xb here, right? So in each row I, you have xi plus some aij bar times xj, where the j's are the non-basic variables. Right? And that's what we did in the simplex tableau, right? So in this case, the aij bar comes from B inverse times n, and then bi bar equals to B inverse times B for the ith entry, right? Okay, this is just to quickly refresh your memory. If you have forgotten about that, just believe me that the optimal solution xi equals to bi bar for this basis, and all those xj non-basic variable equals to 0 for this optimal solution. Okay, and here, if your optimal solution, if all the bi bar are integer, then this solution is integer constrained, right? So that means there must be at least one of these bi bar not being integer, right? So then let's think about how do we use Gomery cut to cut off this inequality, right? Okay, so let's suppose there exists an index h in the basic indices, right, where the right-hand side is not an integer, okay? So we could apply Schratto-Gomery cut to this row where the right-hand side is not integer, right? So you run down the left-hand side, run down the right-hand side, right? This is a Schratto-Gomery inequality. Okay. Now we can add a slack variable to this inequality and keep it to be a standard form, right? Because we want all the inequalities to be equality, right? By adding a slack variable, we can get this equality, and then add this row to the simplex tableau. Okay. Now, any questions related to why these two inequalities are valid? Right. So this is basically picking a linear constraint from the original problem and apply the run down operation. Right. Even if you don't remember the simplex algorithm, you can just believe me that this constraint, the original linear inequality, is a constraint I picked or a constraint that derived from the original linear programming relaxation, and then I apply the run down operation to this inequality. Okay, and then since the left-hand side is integer here, the right-hand side is also integer. I can add a slack variable that is integer here, right? Okay, so if you bet that, you can also derive something like by subtracting the h tableau row from the Schratto inequality. Okay, what I'm doing is as from the, okay, so this is an inequality, the original tableau row from, okay, so the original tableau is this, right? So let's write down the original tableau row is xh plus okay. So I'm just going to take the difference of these two equations. Okay, let's take the difference of these two equations. What we get is, so the xh will cancel out, right? These two things will cancel out. And then if you take the difference of these two equations, what we get is summation over j in n. Plus xn plus 1 equals to okay, so this is just take the difference of these two equations. I get this inequality here. Then now let's define the difference of a hj bar minus the floor of ah bar as fhj, right? So fhj is so-called the fraction of a given number, right? So if you think about ahj equals to something like 3.4, right? Then you take the floor of 3.4, it will be 3, and then the fraction will be 0.4, right? Basically, it takes all the decimals of a number, okay? And similarly, you can define this for b, right? So at the end, you will get this equality here. So the claim here is this equality cuts off the original fractional solution. Right? So let's think a little bit about why that is the case. Right? Remember, what is a fractional solution we had before? Right? We had xh equals to a fractional number, right? And all the basic variables are 0. Okay. So after adding this row, it will make the original fractional solution infeasible. Okay. So why is that? Okay. So it's very trivial to see that, right? Because in the original solution, all the non-basic variables are 0. Right? In the original solution, all the xj's are 0. So therefore, in the original solution, this part is 0. Right? And xn plus 1, by definition, it is a number that is greater than or equal to 0. Right? You add n plus 1 is a slack variable. Okay. And then the right-hand side is a negative number. F0 is a positive number. It represents a fraction of the right-hand side, right? So therefore, you got something. If you take into account the original solution, you got something. The left-hand side is greater than or equal to 0. The right-hand side is strictly less than 0, right? So now you can show this equation cut off the original solution. Okay. But then you can also show this inequality will keep the problem to be dual feasible. Basically, if you add more constraint, it will increase the dual variables, the number of dual variables. That's why it will not change the dual feasibility of the problem. Then you can use the dual simplex to warm start that after you add this cut. Okay. So now it sort of answers your question, right? How do you choose inequality to add a Strato-Gomory cut, right? The answer is you could choose that from the simplex tableau. If one of the basic variable is fractional, by following this procedure, you will be able to cut off that fractional solution. Okay. Now we've already talked about how to calculate a cut for integer linear programs. You can follow this small example here as well. Right? I will not go to the details of this example. You could easily follow that. Right? Now, in the next 20 minutes or so, we will discuss how to derive valid inequalities for mixed integer linear programs. Right? Remember, when we derive the Strato-Gomory cut, we have to rely on the fact all the variables are integer, right? But then you want to generalize this to mixed integer linear programs. So here's a small example to show you how to derive a valid inequality for mixed integer problems. We just have two variables. One variable is x is integer, y is a non-negative continuous variable. And then we have this inequality x plus y greater than equal to b, right? And let's say we define the fraction or the decimals of b, which is greater than 0. You can derive a valid inequality from the fact that x is an integer. This is called a basic mixed integer inequality. Okay. So let's show that real quickly. Okay. Why this is true? Again, the proof is very simple, but it's not so intuitive. You could derive that just using the fact x being an integer variable. Okay, so how do we do that? So consider two cases here. Again, the goal is to derive this inequality from this set here, right? So we know that x is a integer variable, right? So there are two cases that could happen. One is x greater than or equal to the ceiling of b, and then x is less than or equal to the floor of b, right? So there are only two cases. Or in other words, this is like a disjunction here. Either x is, let's say if b is b equals to 3.4, we can discuss two cases. Since x is an integer, x is either less than or equal to 3 or greater than or equal to 4. Right? That's the two cases we are considering. So if x is less than or equal to the ceiling of b, then we have y, by definition, y is greater than or equal to 0, right? So since we have by definition, y is non-negative here. And then since x is greater than equal to the ceiling of b, then we have the ceiling of b minus x is clearly less than or equal to 0, right? Because we are in this case here. And the fraction by definition is f is a positive number, right? Non-negative number, since it represents the decimal places of b, where it is strictly greater than 0. So therefore, the right-hand side is less than or equal to 0, right? You have something greater than or equal to 0 minus something less than or equal to 0, then this inequality holds, right? This is the inequality we want to derive. On the other hand, if we have x to be less than or equal to the floor of b, then you could also show this inequality hold. Okay, so how do you show that? First of all, you just rewrite this inequality as y greater than or equal to b minus x, right? So then we can rewrite b as the floor of b plus f, right? That's by definition, this equality is true. Okay. Then let's see, since the floor of b minus x is greater than or equal to num, this is greater than or equal to 0, right? Because x is less than or equal to the floor of b, right? Now, if you multiply this greater than or equal to 0 number by f, right? F is some number between 0 and 1. Then the right-hand side will be smaller, okay? Then that's why this inequality hold, right? And then you got the result here, right? So this is a very simple proof, just based on the sort of the rounding of x, right? If x is an integer, it can be, let's say b is 3.5, it can be either greater than or equal to 4 or less than or equal to 3, okay? And then you discuss these two cases and derive this so-called basic mixed integer inequality, right? The algebra is not so complicated. You could try to see that later. But geometrically, you get something quite interesting here, right? Where this is a figure where is the original inequality is this line here, and then we have x being integer, right? So therefore, the feasible region is here, this one, and those lines here. And if you plot the valid inequality we just derived, it can be shown that this valid inequality will give you the convex Hall in 2D, right? It will cut off this region that is integer infeasible, right? So if you solve an optimization problem and use the original inequality, you may hit this point where the integrality constraint is not satisfied. After adding this inequality in dashed line here, you see now all the extreme points satisfy the integrality constraints. Yes?
In the last slide, how do we go from floor to ceiling?
How do we go from floor to ceiling? Where is it?
The last line of the inequality. So f plus f times floor of B and
Oh, yeah, so
f
let's,
times ceiling of B.
Okay, so let's write it down, right? So this will be f, let's consider, sorry. So, somehow it activated it. Let's remove this line for now, right? It is nothing but f plus 1 plus the floor of B minus x, right? Then 1 plus the floor of B is the ceiling of B, right? Then you got f times the ceiling of B minus x, right? That's a result. Is that clear? Right. Just because you take the f out, right? So there is an f, then this part should be clear, right? And 1 plus the floor is the ceiling. Okay. Yeah. Okay, so now the last thing I would like to talk about is something called a Gomory mixed integer cut. Right? I will just give you the result without even proving that, because proving that is a little bit tedious. Actually, last year I did teach how to prove that, and then I find most people are lost. It's not worth doing that in class. If you are curious, you could take a look at the proof in the, you can find the slides from last year's lecture. Okay. Now the idea is we want to consider a general cutting plane for mixed integer linear programs, right? After solving the linear programs, again, you will arrive at some optimal simplex tableau, right? Let's assume xb are the basic variables, and then you have xj and yj are the non-basic variables here. And of course, there must be some of the basic variable where the right-hand side is fractional, right? Otherwise, you already satisfy all the integrality constraints. The Gomory mixed integer cut is in this sort of very nested formula. But then you can show that it will cut off the fractional solution. Again, the right-hand side will involve the fractional of the right-hand side. Proving that is not so straightforward, but maybe you could try to validate it will cut off the fractional solution for you. Okay. In this case, probably you could plug in all the non-basic variable equals to 0, and then you will arrive at the fact that you have the left-hand side being 0, and then the right-hand side f0 is a positive number. Right? So you could show that it cut off the original solution. Okay, so here's an example of Gomory mixed integer cut. You could just apply the formula to a given problem and see it indeed cut off the original fractional solution. I would not go to this example in class. As for references, you could check these two integer programming textbook. The first textbook is a bit easier to go through than the second textbook. It did not prove all the theorems we talk about, but in the second one have a more comprehensive proof and then more in-depth topic. Again, it's not possible to cover everything in integer programming just through one lecture, and unfortunately we don't have an integer programming class